Okay, it's 2:02 now. Let's get started. So, hello everyone. Welcome to Ask Seminar series. I'm John, the seminar coordinator. I will be moderating the seminar with our communication specialist, Cassie, and our director, Nas Peter, also join us, and he will be introducing the speaker. And just some housekeeping thing. So this seminar is being recorded, and we will post the recording on the YouTube channel. And after the presentation, we will have the Q&A session. So please feel free to bring up any questions you may have. And we encourage you to speak out using your mic. If you don't have a mic, you can also chat out your questions. Before the speaker gets started, I'm going to hand the ball over to our director, Nas Peter. So Nas Peter, please go ahead.
Thank you very much, John, and welcome to all of you to today's ESSEC seminar, and especially welcome to our seminar speaker, Dr. Pedram Hassanzadeh, who is a professor in the Department of Geophysical Sciences at the University of Chicago. Pedram is also the faculty director for the AI for Climate Initiative, and he's a co-director of the Human-Centered Weather Forecasting Initiative. Pedram received his master's and his PhD from Berkeley, and he was a fellow at Harvard before joining Rice and then ultimately coming to the University of Chicago, where he's been since 2024. And Pedram has a great topic lined up for us, and we can see that also in the attendance here. We are well past the half-century mark, which is a little bit more than we typically get at these seminars. So there's clearly a lot of interest in this. We're going to hear about artificial intelligence, and we all know what Pedram also points out in his abstract, that they can now these neural network-based models can outperform PDE-based models by some metrics of skill out to an extended medium range forecast. So that's pretty impressive. And we're going to hear about some of the limitations, and we are going to hear about something that I have been curious about for a long time that applies, especially if you want to do climate simulations with these. What if you get into something that was not present in the training data set? How does an AI model tackle that? And this is what Pedram and probably others call gray swan events. So I really look forward to hearing what you have to tell us about that. So the floor is yours, Pedram.
Okay, great. Thank you so much for the invitation and for this opportunity to tell you about some of the recent work that we have been doing. As you know, we are going through a second revolution in weather and climate prediction that's driven by AI. And in this area, there are some concrete examples of success, mainly around short and medium range weather forecasting. And there are also some exciting and promising results for longer term climate predictions. And I'll mention some of these. But what I want to talk about today is how about things AI hasn't seen in its training. And the first kind of examples that might come to your mind are about extreme events, in particular, extreme weather events that we know are physically possible, but they are so extreme and strong that we haven't seen them in the training set. And these are events, we are going to call them gray swans. I'll explain why. But these are events that are actually most impactful, and we hope AI can help with better forecasting or better characterizing. Another kind of examples that might come to your mind would be about tipping points. I'm not going to talk about those, but if there is time, I'll tell you about some other examples that can be categorized this way, and you will see that AI models currently have problem with them. So I'm going to formulate what we are trying to do in weather and climate prediction in terms of uncertainties. So as you know, there are three sources of uncertainty when we try to do climate prediction, and two of them are also relevant for weather forecasting. So these are basically epistemic uncertainty, model error, structural error, inadequate representation of physics and numerics, inadequate mathematical and computational representation of their underlying physics. There is scenario uncertainty. Uncertainty is about how much CO2 and other greenhouse gases will be in the atmosphere. And then there's also the internal variability uncertainty. This is basically a signal to noise ratio, the fact that we are giving with a chaotic system. And now we have some nice tools to quantify and visualize the relative contribution of these uncertainties to a given prediction. For example, if you're looking at global mean temperature prediction at different times, or for example, looking at mean precipitation over a given region, we can basically quantify how much each of these would be important. At the end of the day, we know that the more we go to regional scales and the more we look at extreme events, all these three sources of uncertainty will be important. But that's the kind of information we really need if we want to, for example, do climate adaptation. Now, the modeling challenge is that reducing epistemic uncertainty often requires more complex models, higher resolution models that are going to be more accurate, but they are going to be slower, more computationally expensive. On the other hand, reducing the scenario and internal variability uncertainties require models that are fast. So you can look at many scenarios or do long runs, large ensemble calculations. So the challenge is, at the end of the day, we often have to do some sort of make some sort of compromise in terms of which of these uncertainties are more important to us. So since AI, particularly deep learning, came to our field in 2016-17, there has been a lot of interest in whether AI can help with reducing these uncertainties. And most of the efforts initially focus on reducing the epistemic uncertainty, mainly by developing AI-based parameterizations, closures for various processes in the climate system. And there has been a lot of progress in this area. There are a lot of projects around the world focusing on different processes. I'm not going to talk about those, but there are a number of good review papers out there. I contributed 2 of these review papers recently, and over half of each paper is about advances in AI-based parameterization. But since 2 years ago, another direction has been increasingly getting attention, and that's about using AI to reduce these 2 uncertainties, the scenario and internal variability, mainly leveraging the fact that what's called AI climate emulators can be very fast. So as I'll discuss, these models can be used to reduce these 2 uncertainties, and indirectly, they will also reduce the epistemic uncertainty. Now, this shift from reducing epistemic uncertainty to really use the speed of these AI models is really because of this remarkable success that AI models have had in the past few years in doing short, medium range weather forecasting. So here the idea is, rather than solving any PDE, let's just train a big neural network that takes the current state of the atmosphere. So this vector X has velocity, temperature, humidity, every 25 kilometers from the surface to the stratosphere, basically the era 5 grid, and you predict that 6 hours or 24 hours later, you put this back auto-regressively, you can do longer forecasts. And training a neural network is basically all about weighting these weights, finding a set of weights and biases that I'm going to call theta. You can do that by, for example, minimizing a loss function like this. These are basically coefficients in a regression model. Here, we are really looking at the nonlinear regression. This idea has been around since 2017-18, and my groups and a number of other groups tried this. And the progress was mixed until this paper came out. It introduced a model called ForecastNet. This model was developed by NVIDIA, and my group and a number of other groups contributed to this. And here we showed that if you train a model with 75 million parameters on era 5 data from 79 to 2017, you can basically, for many metrics, for several days, 7-8 days, you can get close to the accuracy of IFS, which is the gold standard of numerical weather prediction. While this model, once trained, was 100,000 times faster, over 10,000 times more energy efficient. And soon after that, a number of other tech companies jumped in and basically developed bigger models. with hundreds of millions of parameters. And now you hear about these models in the news all the time. They are doing very well, for example, to forecast the track of the hurricanes. Even at this point, for example, ECNWF agrees that these models are better than IFS. They have developed their own AI model called AIFS. This is the plot from their website. This is the first generation of AIFS they developed. You kind of see that you gain half a day in forecast skill just by switching to AIFS, while again, it's a model that's tens of thousands or even 100 times faster than the NWP. And I would just want to emphasize, it has been a really fast-moving revolution from the time that people started following this idea to the time that basically we got models that can outperform IFS. And now there is a lot of interest in pushing this to subseasonal to seasonal forecasting. We already see some progress in that area. But also there is a lot of interest in whether these models can be used for longer-term climate predictions. Now, of course, weather forecasting is more of an initial value problem, as I discussed. So while the climate prediction is a boundary value problem. So here, one idea is, let's have another set of inputs. I'm going to call them S. For example, if you're building a model just for the atmosphere, this S is going to have the forcing and the boundaries, things like sea surface temperature, land, ice, and other things would be in this S as an input. So now you learn the evolution of the atmosphere conditioned on this S. Now, there also now we have coupled atmosphere ocean AI emulators. So there, this S would represent forcing and everything else that's not in the atmosphere or ocean. But one way that these kind of models can be used for climate prediction is this. So let's say I train one of these emulators with data from a bunch of very high resolution GCM simulation, physics-based simulations with different forcings, different S. Let's say I can do 10 to 50 years of these kind of simulations. I train the neural network. And once it's trained, it's going to be very cheap to generate a lot of data with this model, even for an unseen S, as long as this S is sort of an interpolation between the ones the model was trained for. And so now I can generate a lot of data. I can use this to, for example, examine how extreme events might change in different regions. So using these AI emulators this way, we are going to reduce the internal variability and the scenario uncertainty. Of course, this emulator is not going to be more accurate than the GCM, but again, because now from a GCM, I just need much shorter simulations, we can also go to more expensive and more accurate climate models. So this is one idea for how these models can be used for longer-term climate predictions. Now, of course, all of these hinges on two ideas. One is when I run this model for a very long time, the flow, the climate would remain physically consistent. It's not going to drift and produce anything unphysical. More importantly, and something that's very important for extremes, is that the model that is trained on a short data set is going to produce information about the extremes beyond what it has seen in the training set. So just because I have 500,000 years doesn't mean I have more information about the extremes than what was available in the 50 years. So if I take a linear function and sample it 1,000,000 times, at the end of the day, I have learned a linear function. So if I want to use these models this way, these models need to have more information about details when I do longer emulations. So in my group, in the past few years, we have been basically building a hierarchy of test cases to look at these kind of questions. That basically the hierarchy goes from simple systems like Lorentz all the way to turbulent flows to weather and climate data. And we use this the same way we use a climate model hierarchy, trying to find a balance between understanding and scalability as we develop new ideas. So in the presentation today, now I'm going to focus on that second question. And specifically, I'm going to look at this question. Can AI models predict events that are rarer and stronger than what they have seen in the training set? Now, I'm going to call these kind of events gray swans, borrowing from the term that was used by Kerr Emanuel and Ning Lin in a very nice paper they had a few years ago about tropical cyclones in a changing climate. So in the context of AI for climate, gray swans are basically events that are physically possible for a given climate, for a stationary climate, But just because they are very rare, we haven't seen them in the training set that we have. So just try to visualize this. Let's say I have 40 years of era 5 data, but if I had 1,000-year observation of the same system, now there would be events that are stronger and rarer, and these are the gray swans. These are different from black swans, events that are basically maybe happens once in the age of the universe. I don't expect the models to forecast these, but gray swans are really the events that we hope the AI models can forecast and characterize because they are very impactful. So now, depending on who you ask, people might tell you that the AI models can do this or cannot do this. People who say they cannot, probably they'll tell you that, well, we all know about what's called data imbalance. This is basically events that are not frequent. When you try to do a statistical learning, when you try to learn things from data, you are not going to learn them. Remember that training a neural network is all about this loss function, right? So events that are infrequent, maybe they happen one every 1,000 samples, they're not going to increase this loss function much. So we are not going to, during the training, this data is not going to be adjusted to learn them. So it's called data imbalance. These gray swans are sort of the asymptotic limit of that. These are events that had zero contribution to the loss function. So very likely the model didn't learn them, cannot predict them. Said in a different way, basically, if you want to get the gray swans, you need to extrapolate at the tails of the distribution, which generally we know AI models should not be expected to do that. On the other hand, some people might tell you that, well, these AI models might be able to do this because there is growing evidence that these models are not just memorizing some patterns. They're actually learning some dynamics. And there have been some nice papers, especially by Greg Hakim, doing like kind of looking at some controlled perturbations that they impose to some of these models. There are also now some papers with Green's functions experiments that, again, they show that these models are learning something about the dynamics. So people think that, well, because you have seen weaker events, you can learn from them and predict something stronger. So in our work, trying to answer this question, we started by looking at a specific event, which is this rainfall in Dubai in 2024. If you remember from the news, this created a lot of flooding in Dubai. And if we look at the distribution of rainfall during the training time period of these AI models, this is the distribution. This is where this event was. So this was almost twice more rain than any rain that these models have seen during their training. So the question is, can these models, some of these state-of-the-art AI weather models, forecast this event, which is basically a gray swan in this region? So I'm going to have a sip of my tea, and I'll let you think for a few seconds about whether you think the AI models can forecast this event or not. Okay, so it actually turned out the AI models can do a fairly good job in forecasting this event. So this is just a movie. Again, for now, we assume everything in era 5 is the truth, even the precipitation. So this is era 5 precipitation, that's the shading. And this is it's era 5. This is one of these model graph gas. And you see that the model does a good job getting the timing right, the location right. I can make a time series of the rainfall over Dubai, that's shown here. The black line is era 5. The dashed line is the most rain the model has seen during its training. And you see that the blue is GraphCast, it's like for a 5-day forecast. So every point here is like a forecast from 5 days earlier. And you see the model actually does a good job in getting the timing right and even getting the amplitude rather well. And again, it goes well beyond what was in the training set. There is a second model here, Fushi, which also does everything right except that the amplitude is lower. And in the paper that's under review, we actually have done a full analysis of this event. So it's not just that there's a time series that is captured. It's actually most aspects of the event are captured pretty well 5 to 8 days ahead of time by these models. So we're a little surprised that the model actually can do a good job with this. Now, at the same time, Chiang, who is a research scientist in our group and has been leading that paper, he was doing another study with a number of other collaborators. And here, we were doing controlled experiments with that model I mentioned, ForecastNet, where we actually removed some of the extreme events from the training set. So what we did is we trained 5 versions of ForecastNet just by changing the random seed of the weights of the neural network. We trained it on the entire data set that's usually used for the training from 79 to 2015. I'm going to call that ForecastNet full. We also trained a version of the model where from the training set, we removed any sample that included a category 3, 4, 5 tropical cyclone anywhere around the world. I call that ForecastNet no TC. This is the model that has never seen a category 3, 4, 5 tropical cyclone. By doing this, you actually lose 25% of the data. So for control, we also trained a model we call ForecastNet Rand, where we randomly remove 25% of the data, but we make sure that all category 3, 4, 5 storms are in the training set. So now the question is, can this model, the NoTC, forecast category 5 storms, which are basically the gray swans for this model? So first, I'll show you the results with ForecastNet Full and Rand. So here, this is an example of Hurricane Lee, which was a category 5 storm in 2023, so out of sample. The black line, this is the pressure at the center of the storm versus time from era 5. Again, here we assume era 5 is the truth. The model is trained on era 5. We test it against era 5. And the blue shows the basically forecast from a bunch of perturbed initial conditions with ForecastNet, which actually you see the model does a good job. The dashed line here, this is that boundary between category 2 and 3, and this is the boundary between category 4 and 5 in era 5. So the full model and even the Rand model, which has 25% less data, do a good job in forecasting this event. So now the question is, can NoTC forecast this gray swan? So again, I'll give you a few seconds, just think about whether you think the model can do this or not. Okay, so it turned out the model actually cannot forecast this event. So when we initialize the model, it actually predicts a weakening storm, and then sort of you see that it saturates around the boundary between category 2 and 3. And we repeated this with 20 test samples of category 5 that we had, and the story is the same, whether we initialize it before it reached a category 3 or after it reached a category 4, we always see that Full and Rand do a good job. The NoTC basically always saturates. And notice that the model, the NoTC, actually gives you the worst kind of error. It gives you a false negative. It tells you there is a category 2 storm coming, even though you are getting a category 5 storm. So we started wondering, well, what's the difference between these and the Dubai work? Of course, we are looking at different phenomena, precipitation versus tropical cyclones. We are looking at different models. But overall, all these models have the same learning principle. So we thought to do another set of experiments with this ForecastNet model. So we trained 2 more versions. One is called No West Pacific, No North Atlantic, where basically here, we trained the model on a training set where we only remove training samples that had category 3, 4, 5 over the Pacific or only over the Atlantic. So the model has always seen category 3, 4, 5 storms over one of the ocean basins. And I'm not showing the results, but it turned out that now the model can predict, these 2 models can forecast category 5 pretty much everywhere with accuracy that's almost as good as the model, the Full or the Rand model. So it seems that the models can actually learn from category 3, 4, 5 in other regions. Now, going back to the Dubai event, now this event had a rather simple dynamics. It was an extratropical cyclone coming and generating rain. So we created the distribution of the rainfall from dynamically similar events in the training set. And that's shown here. So now we see that this Dubai event was not anything special in the training set, because in other regions of the world, there were events with very similar dynamics that were generating even more rainfall. And again, we started thinking that these models can actually learn from other regions. Now, we have done a bit more work trying to look at this process that we call translocation, learning from other region. One thing we did, we started looking at the adjoint, or what's called the receptive field of the AI models. So remember, this is the AI model. you can take the derivative of the neural network with respect to any input that's sort of built into the algorithm. And what I show you here is the derivative of the rainfall over Dubai with respect to vertical velocity or humidity. This is for just a 6-hour forecast. And what's interesting is that when the model forecasts the rainfall here, of course, as expected, it uses local information a lot. But even beyond that, it sort of uses information from other regions around the world very far away. Now, there's nothing physical here, so you don't expect over 6 hours something here affects the rainfall over Dubai. But this is actually something that is because of the algorithm that is used, which in this case was a graph neural network. So you kind of see the graph and the fact that these are very deep models. So basically what this says is that when the model was being trained, when it was learning to forecast rainfall over Dubai, it was always looking at pretty much other places in the world as well. So it could learn from other events, stronger dynamically similar events that were in other regions. We have calculated this receptive field for another model. This is the AIFS, the model from ECMWF. Now you see that the receptive field is different exactly for the same thing. But again, when you look at the paper, this is again because of the architecture that the model had. What it has is still, when it is doing a forecast over Dubai, it actually uses the entire mid-latitude of the northern hemisphere. So again, if there were events in other regions, the model would learn from it. And generally, we have found this use of this adjoint or the receptive field of these models to be very useful in understanding what they are doing. But we argued in the paper that it is likely that the models learn from other regions because of the global or at least non-local receptive field that they have. So what I have told you so far is sort of summarized here. What we find is that these AI models cannot extrapolate. They cannot learn these global gray swans. They basically cannot learn from category 1 and 2 tropical cyclones and forecast the category 5 storm. They cannot extrapolate. However, what was surprising is that these models seem to be able to translocate. So they can learn from similar events, dynamically similar events in other regions and apply it to another region. And I keep emphasizing dynamical similarity because we really think that you need to have events that are dynamically similar. For example, for the tropical cyclone case, in the extratropics of the NOTC model, there are still storms, extratropical cyclones that have very low pressure, but the model could not learn from that. Now, of course, we know the dynamics of the tropical and extratropical cyclones are different. So as a physicist, you can think that's the reason. Of course, the AI model doesn't know anything about the physics, but when you look at some of the joint distributions of, for example, wind and pressure, you know that it would be different between a tropical cyclone and the extratropical cyclone. And again, we think that that's how the AI model would know about dynamical similarity. Now, here, the results I showed, which are in these two papers that one is published, one is under review, we look at some specific models, and of course, this is because of the computational constraints. ForecastNet is the only model that's cheap enough that you can train many times, with the resources that we have. But we argue that basically these results would apply to any of the current state-of-the-art models because they really have the same learning process. They all use what's called supervised learning, and they are all focused on the fast dynamics. They all learn from this evolution of the prognostic variables over 6 hours or 12 hours. Now, before moving forward, you might ask, well, how many of these gray swans did the model have to see to be able to forecast gray swans? So we had a great intern from UT Austin this summer, and what she did was she started fine-tuning the model with 1, 5, 10, 20 of those samples that included category 5 storm that we manually excluded from the training. And fine-tuning basically means you have a few new samples and you want to do a few more epochs. So you continue the training of an AI model and you update the weights a little bit. And what she found was that even with 5 samples, you can actually hugely improve the NOTC model. And with 50 samples, you actually get a model as good as the best model that we got by training on a lot of data, which is quite interesting and quite promising that you just need a few samples of these gray swans to get a model that works for them. And now we are doing some work in trying to understand what changes inside the model, how the weights change, that they actually adjust to these very few samples that they see with the extreme events. Okay, so far, I only talked about short-term forecasting, but I tried to motivate the work based on some of these questions in long-term climate prediction, that you train the model, the AI model, on a small amount of data, and then you do a long emulation, and that whether that has more or less information about the extremes than what was in the training set. Now, we cannot test this using Arrow 5 because we just have, the 40, 50 years of Arrow 5 that we have, but we can test this in climate models that we can run for a long time. So in this work that's in collaboration with a group of Freddy Boucher in ENS Paris and was led at UChicago by Alice Wickner, who is a graduate of physics department at UMD. So we used the intermediate complexity GCM called PLASM. So this is a model that has a decent atmosphere. It has a prescribed ocean. It has a simple model for land, simple model for ice. But it's cheap enough that you can run it for a very long time. So we did almost 100,000 year integration of the GCM. This would be our ground truth. We took 100 years of the GCM data and we trained 2 AI models on it. AI models that are trained with things like SSD and land and other things imposed in this S. So we use 2 architectures. One is this spherical neural operator, Fourier neural operator, and the other architecture is a transformer architecture. And so we trained these 2 emulators, and these are emulators that are stable. You can run them for a very long time. So from each emulator, we also generated almost 100,000 years of synthetic data. So now the question is, if I look at the extreme events in the ground truth and in the emulation, how much do they agree? So here I'm just showing you an example. This is precipitation over Florida. The black line, and this is the return period. So the black line, this is from the ground truth, from this 100,000 year integration. The red triangles, this is from the training set, which was just 100 years. So this is the most rain that these emulators have seen over Florida during the training. And the blue and the green, these are from the emulations with the 2 emulators. And the dashed lines here, these are the GeV fit from extreme value theory. Now you see that the emulator actually can generate events with some more rain than the most rain they have seen, at least in this region. And they are better than the GeV fit in telling you the return period, but still they can be off by a factor of 10 or even larger. So in some sense, this is promising, but also it seems that if you just want to use the current emulators to train them on a small amount of data and then run them for a long time and get return period curves and things like that, they're not quite ready to do that. And we can discuss where this kind of shortcoming comes from. Part of it is the fact that regionally the models have biases. These models are trained to reduce the global error. And then you can see that depending on which epoch of the model you choose or when you choose change the random seed, the biases can be in different places. And so some of these differences come from the regional bias in the climatology and in the variance, but also notice that this is a lot to ask from these models because basically not just to produce events that are stronger than what they have seen, they need to get the frequency right, meaning they need to get the larger scale circulation and sort of the preconditioning of the extreme events correctly. They need to get the relationship between the larger scale circulation and the extreme event correctly and produce everything in the right frequency, which again, it seems that these current models trained with a simple loss function, this supervised learning, focus on the fast dynamics, are not quite ready to do that. But again, I think they're doing better than what was expected. And these results, we are almost done with the paper that report these kind of analysis for heat waves and coldest snaps in different regions. And we show results when you debias the models and things like that. Again, you see the results are kind of mixed in whether these models can capture everything that we would need, for example, to inform adaptation. Now, To address some of the shortcomings of these models with extremes, one direction we are pursuing is to combine these AI models with some mathematical algorithms that exist for rare events, specifically what's called the rare event sampling methods, or RES. So these methods have been around in climate science for a while. For example, the idea behind one of these methods is, let's say I have a physics-based model, I generate an ensemble, I do basically a simulation for a couple of weeks. And then here I stop. And if I have a way to know which of these ensemble members is going toward an extreme event, for example, a heat wave, and which one is not, I can terminate the one that's not going toward a heat wave, and I can clone or branch out from the one that is going toward a heat wave, and I can repeat that and basically nudge the climate model to go toward part of the phase space that there's a higher chance of getting stronger heat waves. And this approach has shown a lot of success with some kind of events. For example, there's this really nice paper by Francisco Ragune and Freddy Boucher that they basically showed that if, for the same model that I mentioned, PLASM, if your computing budget is 1,000 years, you can actually use that and get return periods of heat waves. These are basically hotter than normal summers that have return periods of thousands or tens of thousands or hundred thousands of years. And now there are also a number of nice papers from groups in ETH, other places, with ensemble boosting and methods like that, again, very much along the same line of this RES approach. Now, the problem with this approach is that you need what's called a score function. You need something like a scalar that tells you, when you look at these different ensemble members, which one in a few weeks or longer would get to a heat wave and which one will not. And so for some kind of events, like a hotter than normal summer, that is sort of not that difficult to get. But for things like precipitation or blocking driven heat waves or a lot of very impactful events, that's actually not that easy. So in this work, that again is collaboration with Freddie and Jonathan Weir and a couple of other people, and we have a paper that's on the archive, we coupled these AI weather models with the physics-based model. So the way that this approach that we call AI RES works is, again, you'd use a physics-based model to generate an ensemble. When you stop here, rather than using a simple score function, you actually do a probabilistic forecast with the AI model. So the AI model is fast. It has a skill for at least 2 weeks. So you can generate an ensemble, and you can use this AI-generated ensembles to calculate a score function, which will then guide your physics-based model. The nice thing about this approach, which is really a hybrid physics-AI approach, is at the end, the samples of the extremes and the return period curves will come from the physics-based model. And again, in this paper, we showed that when you look at heat waves, this approach actually works fairly well. And of course, one thing that can be done now is that now I have generated events with the physics-based model that are stronger than what I originally had in my training set. I can now use these to fine-tune the AI model. So eventually I get an AI model that has seen more extreme events, even has seen the gray swans, and a physics-based model that more efficiently would give me more extreme events. One thing I should mention is that at the end of the day, I strongly believe that to train an AI model, you will need training samples that come from a physics-based model. And I think this is the best way to get that for the tails. We have some work that, for example, you can use a generative model that is trained on a small amount of data. You use that to generate a lot of samples. You use that to train the AI model, and you see that iteratively that would lead to what's called the model collapse. Anyway, I just want to mention that. I'll be happy to tell you more. Anyway, so just to mention a couple of other things. So far, I only talked about extreme events, but let me tell you about another kind of phenomenon that is still, you can categorize it as something that AI model hasn't seen, and it's not necessarily an extreme event. So now there are a couple of emulators. One is from the Allen Institute, it's called ACE2, and one from Google, it's called Neural GCM. They actually can do AMAP kind of simulation. You have imposed SSD from ERA 5, and you run these models, from 79 to 2024. And these models have great troposphere. People have already shown, if you look at MJO, if you look at other things in the troposphere, they do a really good job. But here in this paper that was led by Ian Baxter, who's a postdoc with Tiffany Shah, what we did, we also look at QBO. So as you know, if you look at the tropical stratosphere, and we look at the zonal mean zonal wind in era 5, every almost 2.5 years, the wind changes direction. So that's the black line that's shown here. Physics-based models, we know that they have problem with getting QBO correctly, because this is basically, these require the good parameterization of gravity waves and convection. So physics-based models that are shown here, they have problem with getting QBO. But also the AI models have problem with QBO. So here I'm showing you the ACE2 upper level wind. It does some fluctuation, but it's not QBO. It doesn't have the right period. And this is in neural GCM, which sort of, it's locked in one phase, and the model doesn't switch the direction of the winds. And then sometimes you get this abrupt change. We believe that the problem here is that all these models are trained with this kind of loss function. They're trained to learn weather. They're trained to learn the fast dynamics, and they do a great job with that. But then something that in the upper troposphere changes every 2.5 years, that's not going to contribute to this loss function. So as a result of that, this model never learns that, well, there is something that I'm not learning, so I should adjust my weights so that maybe I generate some gravity waves and fluctuations in the troposphere so that I can drive a QBO. So again, there are now ways to solve these kind of problems, but generally what we found in this paper is that these models also have problem with fast and slow dynamics, which this is one example of that. There's a second example in the paper. So to wrap up, so far I tried to tell you about some of the shortcomings of these models. But I want to finish by emphasizing that I think these models are actually quite remarkable. I think these AI weather models and increasing the climate are one of the biggest achievements of AI in science so far, and they're already extremely useful. So to give you an example, so this summer, we at University of Chicago, in this human-centered weather forecast initiative that we have, collaboration with a number of other groups and tech companies, we worked with the Ministry of Agriculture and Farmers Welfare in India. And we sent 38 million farmers for 30-day forecasts of the monsoon onset that was generated with AI models. So in this work, we actually benchmarked some of the existing models and NWP models from 1965 to 2023. We found 2 of these models, the AIFS and neural GCM, to actually have fairly good skills in forecasting the rainfall and the onset of the monsoon with a definition that was motivated by what the farmers need. We blended them into a probabilistic forecast, and we shared them with the ministry, who then turned them into SMS messages and sent them weekly. Now, it turned out this forecast was fairly accurate. This year, the monsoon had an interesting behavior that it started early in south of India, in Kerala, and then it stopped moving. It basically stalled for 3 weeks. It paused, and then it moved. And the AI forecast captured this fairly well. Other models also captured it well, but the forecast that we had that was weekly shared with the farmers were the only forecast that actually warned the farmers about this pause. And we have, from the surveys, we know that the farmers who paid attention actually benefited from knowing that there is a dry spell coming and acted accordingly. And so now we are expanding this work to benchmark these models over Africa. And we are also expanding the work over India in collaboration with the ministry and IMD and ITM. Okay, so with that, I think it's a good place to wrap up. So I think these AI weather and climate models, I think are quite powerful, quite promising. But as we expand their use, I think there are a number of questions and challenges and opportunities that we should think about. And some of them are listed here. In this talk, I mainly talked about rare events and a little bit about this multi-scale dynamics, but I think there are a lot of things here that I think are quite interesting. And I think the way to make progress is to further and further integrate AI theory, apply computational math, and of course, the physics of climate and fluid dynamics into the analysis and into building the next generation of these models. So I stop here and looking forward to your questions and comments.
Thank you. So if you have a question, you can go ahead and raise your virtual hand or just let me know in the chat that you have a question. There's one. Isaac, go ahead.
Yeah, thank you, Pedram. This was very interesting. At least you didn't try to sell us everything that, AI can solve all the problems. So I appreciate that. I work at the NASA Global Modeling and Assimilation Office. We have a monitoring team. We have a meeting on Friday. We get down really when we are doing the evaluations to individual stations, a small region that, it snowed here, but it didn't snow there. The temperature was a Kelvin above, like the observed here. So most of the AI evaluations are really based on this big picture, and you show also one for the Dubai, but it was really, this very big synoptic system is moving across the Persian Gulf, and even you show like some examples from the rainfall, which I believe it was actually it predicted the rainfall for some time, and then for the second day it didn't continue. So the error of five, your real time, your physics based is showing that the second day of rainfall that the AI missed. So what happens if you really get down to the pixels and the grids and try to evaluate the AI results based on not just only the anomaly correlation, the real variables like temperature, snow, rain, water vapor, wind, what would happen? Do they really look comparable to the physics-based models, or they are just good in giving us that big picture? Thank you.
Yeah, thanks. I mean, that's a great question. And, I think the papers now coming out that people try to do their best in evaluating this model, probably better than me what they find. But one thing that I learned from working with some of our econ colleagues at U Chicago is that there are things that are useful to forecast, and they may not be about what happens exactly at the grid point. So the index, the definition of the monsoon that we used in this work is actually based on a paper that some colleagues at U Chicago in the public policy, Amir Jinnah, who is mentioned here, and Fiona Berling did before that. Even like a definition of the Indian monsoon that's more about where the large scale wind starts and when whether there is a dry spell after that or not. That to the first order is something that can benefit farmers a lot. And Michael Kramer, who is an economist, they do kind of back of the envelope calculations, and based on the other information they have, the gain can be a factor of 100 or even larger just by providing that kind of forecast. So my point is that there are things that these models can do that they can be extremely useful. But also I agree that, for a lot of other things, these models are not ready. Again, they are very limited in terms of the resolution. You need to have high quality data for the training. But again, there are things they can do, and they have advantages over NWP. But I think, of course, as a community, we need to continue developing, both of these. I should say there's a lot of interest in downscaling. Even, for the Indian monsoon, there's a lot of interest in can you provide a forecast on like just a couple of kilometers. But then I think for us, the concern has been about the quality of the data for validation, and then any kind of data that would be used for the training. So I don't know whether this answered your question or not, but I mean, I totally agree that much more work is needed to understand the limitations of these models and how they can complement, NWP models.
Yeah, thank you so much for the explanation. Thank you.
Do we have any other questions? Go ahead, Mark.
Hey, Professor, thanks very much for your time. Enjoyed the talk. I've got something that's a little more nuts and bolts, and maybe it's a little out in left field. Can you talk a little bit about the computational environment that you're working in?
Sure. You mean to just do inference or to train any of these models?
Either way. I'm curious if this is all CPU based, if you're using any GPU, just what the order of magnitude is as far as the systems you're working with.
Yeah, I mean, these are all GPU. Even inference of a trained model on CPU can be quite slow. So everything is done on GPUs. for the inference, like for example, for the monsoon work, we set up 3 systems because we were doing real-time forecasting. So we really needed to have, backups. We did clouds and we did some of the existing U Chicago GPUs. But like I can give you a number, like the entire cost of doing the monsoon forecast over several weeks was $150 on cloud. But these are all done on GPUs. Now for the training of the model, these models can be quite expensive. They're not as expensive as LLMs, but they are still like beyond the reach of at least like, for us at U Chicago. ForecastNet that we train, um, I'm not sure about exact numbers for that, but again, it could be like several GPUs for several days to do one set of training. And then the more complex models, the state-of-the-art models, you might need 200 GPUs for 7 days to be done with one set of training.
Wow.
Yeah. So again, they can quickly become quite expensive. And then, the generative models like diffusion models, even the inference can become expensive and slow.
Are these resources that your unit has at their disposal, or are you using, Greater Chicago resources or?
We have some nodes that we have at U Chicago, some GPUs, but for training anything beyond like ForecastNet, it's very difficult. I mean, you can fine tune the model, you can take a model and update it a little, but training from scratch, given that tens of times you need to change the parameters and do all kind of evaluation, is quite difficult. And I think that's why a lot of the development of the state-of-the-art models have been at tech companies because of the GPUs and also just the expertise to optimize the code and make them efficient, which is very difficult for us.
Great. I really appreciate the answer.
Yeah, go ahead, Zihao.
Hi, Professor. I'm a PhD student in the geographical science at the UMD. So we also have an emulator for the carbon forecasting model. So we have the ecosystem dynamically model. It's called AD, and we developed deep AD version for forecast carbon simulation from the past to 2100 years. So when we're doing design the models, design our own emulators, like we tried several benchmark models, for example, the Fourier FNO, Fourier neural network, and also the spherical Fourier FNO. And we also tried a bunch of other transformer-based models. So we realized that when we generalize this climate-based, more like a climate design emulator to our terrestrial carbon forecasting problem, we feel we found that the performance of this transformer is has a similar performance like the recurrent neural networks. So I was curious about do you design some emulators by your group self for a certain, real event exam specifically, or you I saw some state of art models designed by the companies, or you guys more prefer to use that models, and also the generalizability of these emulator models in different downstream tasks.
Yeah, I mean, so far, like the kind of emulators that I showed, we try to use the emulators that, the kind of infrastructure that's available, like the spherical Fourier neural operator and the Pangu, the transformer. Like we use what's available. We have been playing a little bit with the loss function and the way that the training is done. But again, I mean, these models can become pretty big and expensive, right? And it's like the memory and the GPUs that becomes a major issue. So we are mainly using trying to build on the existing infrastructure when it comes to these algorithms.
Okay, thank you.
But I think one thing to keep in mind is that all of these comes from algorithms that are pretty physics free, right? I mean, the transformer, the diffusion model, these were first developed for other kind of applications and then came to our field, right? And people use them for turbulence and PDEs, and we use them for climate. So I mean, down the line, it is possible that we can develop better physics informed architectures that better respect the properties, especially the multi-scale aspects of our data. But again, this can be slow, and usually you have to start with a simple system and scale it up. It takes time. Right.
Thank you so much.
Thanks.
Any other questions while we still have our speaker? Go ahead, Isaac.
Yeah, just going back to what Mike asked about the computing resources. So if I understood it right, like so in terms of uh, like the hard disk and memory, and I understand like for physics-based models, those resources are huge, really. Like I have 500 terabyte of storage, and still keep complaining that I need more storage. Uh, so how much do you, let's say if you want to really train one of these models, because you actually need to get all that error 5 data to be able to train it for a period of time. So how much data do you need in terms of storage, I mean, and memory and resources like that? Is and if you want to use, let's say, AWS, is it really uh, possible for like grant-based works that we do to have access to those resources, or is this something that you really need to have your own local? And I know why Mike actually asked that question, and that's the same reason I'm asking this question as well.
Yeah, I mean, it would be hard for me to, come up with the specific numbers, but I think for us, the biggest problem is the memory of the GPUs during training. Because now another thing we want to do is that we want to train probabilistic models where, during the training, you want to generate several ensembles, members, right? And then evolve them for several time steps and calculate the CRPS and things like that. And makes that put significant constraints on the GPUs. Now, again, I think for CPUs, now we have, parallel computing, and we really know how to use thousands of CPUs together. For GPUs, that's just much more difficult. At least, in our group, we try to just take one node and within that node to use the memory. But of course, you can have several, like a code that's more parallel and uses a bunch of nodes. But again, those things are just much harder to develop again with the resources at the university. So really, I would say like the biggest constraint, at least for us currently, is the memory of the GPU, rather than necessarily the storage for the data or anything else.
Yeah, thank you. It was a very nice talk, and I meant Mark, not Mike,
Yeah, thank you.
our IT director.
Sure, thanks.
Go ahead, Jin.
Yeah, I want to ask a question about the relate to QBO. So you mentioned the physical model and the AI model, they cannot get the QBO correct. So my question for you, you mentioned about the loss function. What kind of things missing, say, either in NWP or AI model that we cannot catch, and then the loss function can catch?
Yeah, that's a good question. So I think to be clear, I'm not saying that the reason that the AI model and the physics-based model don't get QBO is the same. I mean, again, I think they're both related to representing the gravity waves. But in the physics-based model, I mean, it could be part of the problem with the convection parameterization, right? That would be the source to the gravity wave parameterization. But for the AI models, which again, I mean, they don't have any of these, they don't have any, this model, the ACE2, doesn't have parameterization. It just implicitly learns the smaller scales. The problem is that the model has only learned 6-hourly evolution, right? So anything that increases this loss function, when you do a 6-hour forecast, the model would figure out to move these hundreds of millions of weights it has, right, to fix that problem. And they do an amazing job in that. But then something that, I mean, the zonal mean zonal wind at like 50 hectopascal would barely change in 6 hours, right? So then that would not contribute to the loss. And so the model doesn't learn anything associated with that. So I think this is sort of at the heart of this problem. This is a problem you can also imagine if you try to couple land or to couple ocean and deep ocean. But again, there are components that are slow and there are components that are fast. So the question would be how to actually learn them together. So I think, and again, there are methods like reinforcement learning and some of the other ideas that could be potentially used. But the question is how to learn the slow dynamics without losing the fast dynamics.
Yes, thank you.
Thank you so much. So does anyone have any more burning questions? We're at time, but if somebody has been waiting, this is the time to ask.
So I got one question. It's a very great talk. So a lot of people are talking about explainable AI. How do you make it more transparent and interpretable for like model prediction, decision making? And I really like the way you explain how the neural network model is learning from not just the local areas, but areas out of the local areas. So, what's your suggestion for to make the AI model more explainable? Like what I know there are a number of methods such as destination method or some feature attribution method. So what is your suggestion? What's your take?
Yeah, I think I think that is something that I think very exciting to be able to better understand how these models learn and what they learn and why, because they're certainly doing something very interesting just from data and how they do that. Uh, I think that is a very interesting question. Um, I just think that the methods that are currently available for explainability and interpretability, I mean, because they're mainly developed, focus on how the optimization of these models are done, or generally they're developed for all kind of applications. They're not necessarily tailored to tell us something about these kind of models that are applied to a physical system. For example, a lot like our variables, they're all correlated. Our scales are highly correlated, right? So to kind of disentangle these with the current methods, I think that's just quite difficult. Like what I showed here with this, looking at the adjoint, I mean, this is related to a lot of these ideas, like called LRP and things like that, that are used in explainable AI. But again, it's not quite easy to get the kind of explainability that we like in physics, in physics, climate science, to get out of that kind of approaches. So I think that's another area, to develop explainability methods that are tailored toward explaining these kind of models. I think that's a great area of research.
Thanks.
Thanks.
Hey, thank you, everybody. I'm going to go ahead and let our speaker go, but thank you all so much for attending this. And thank you to Pedram for giving us this great talk, very timely. I got some questions in the chat about the recording. So just FYI, I'm going to try to get the recording up by tomorrow afternoon. So that will be on the ESSEC YouTube channel. And another reminder is that we will not have a seminar next week for the holiday, so we will resume the week after. So thank you all so much. Have a great afternoon. Thank you, Pedram.
Thank you. Bye. Thank you.